Hello, this is Richard Hammack's Calculus 1. We are in part 5 of the course on integration. Most recently, in lecture 42, we introduced the Fundamental Theorem of Calculus. It's a big topic, so today in lecture 43, we'll have more to say about the Fundamental Theorem of Calculus. You'll remember that the theorem comes in two parts, part 1 and part 2. And it's really part 2 that's the most useful for us. It gives a formula for definite integrals. Our plan today is threefold. First of all, we'll look at more examples of part 2 of the fundamental theorem. And secondly, we'll look at a useful interpretation of part 2 of the fundamental theorem of calculus. And finally, we're going to go back to part 1 of the fundamental theorem and look at that as a derivative rule, as our last derivative rule. So let's go to the first item on our plan and look at some examples of part 2 of the fundamental theorem. Here's a quick reminder. The fundamental theorem of calculus part 2 states that if little f is continuous on the closed interval from a to b, and big F of x is any antiderivative of little f of x, then the integral from a to b of little f of x dx equals big F of b minus big F of a. That difference is abbreviated this way, which we read as big F of x from a to b. It's just a notation that stands for big F of b minus big F of a. So again, the fundamental theorem of calculus part 2 gives a formula for finding definite integrals. Let's look at our first example. We'll do the integral from 1 to e of 1 over x dx. According to part 2, all we need to do is find an antiderivative of 1 over x and go from 1 to e. Well, an antiderivative of 1 over x is easy to find. The integral of 1 over x dx is ln of x. So by the fundamental theorem of calculus part 2, this definite integral equals ln of x from 1 to e. So we plug in the e to ln of x, subtract off what we get when we plug in the 1. The answer is ln of e minus ln of 1. Well, ln of e is 1 and ln of 1 is 0, so the difference just equals 1. The definite integral from 1 to e, 1 over x dx, equals 1. Our function in this case, 1 over x, is positive on the interval from 1 to e, so we know we can interpret this definite integral as area. Here's a picture of the relevant area, the shaded region under the graph of 1 over x between 1 and e. Since the definite integral equaled 1, we see that the area, shaded area here, is exactly 1 square unit of area. Next example. Let's do the integral from 1 to 2 of 3x squared plus 4x minus 1 dx. The fundamental theorem of calculus says we just need an antiderivative of 3x squared plus 4x minus 1, and we'll evaluate from 1 to 2. Well, that antiderivative is easy to find. We just take the indefinite integral of this integrand, which is 3x cubed over 3 plus 4x squared over 2 minus x. And we evaluate from 1 to 2 here. So before plugging in those numbers, let's simplify a little bit. The 3's cancel, 2 goes into 4 twice. So we get x cubed plus 2x squared minus x from 1 to 2. Plug in the 2, you get 14, minus what you get when you plug in the 1, that's a minus 2. Answer is 12. Next example, integral from negative 1 to 1 of 1 over x squared dx. According to the fundamental theorem of calculus part 2, we just need to find an antiderivative, big F, of this function 1 over 1 plus x squared and go from -1 to 1. That antiderivative you can get with an integration formula. The indefinite integral of 1 over 1 plus x squared dx is the function tangent inverse of x. So our answer is going to be tangent inverse of x from -1 to 1. Plug in those numbers, those limits of integration, and we get this difference. Tangent inverse of 1 is pi over 4. Tangent inverse of -1 is negative pi over 4. So our answer is pi over 2. How about the integral from 0 to pi of cosine x dx? It's so easy. Part 2 of the fundamental theorem says all we need is an antiderivative of cosine of x, which would be sine x plus c, but of course we can set the c equal to 0. So big F here is just sine of x. And we evaluate from 0 to pi, so that's sine of pi minus sine of 0, and both of those signs are 0, so our answer is 0. So this definite integral equals 0. I want to pause here and indicate that that actually makes a lot of sense. We've got the integral from 0 to pi cosine x dx. Let's draw the graph of cosine x between 0 and pi. It starts at height 1, at pi over 2 it's 0, and by the time you reach x equals pi, cosine of pi is -1. So you see here in the shaded region, a up and a down appear to be exactly equal. They counterbalance each other. This integral would be a up minus a down, which is 0. So this answer of 0 is not surprising. Let's move on to our second goal for today, which is an interpretation of the Fundamental Theorem of Calculus, Part 2. And I'll put it in this blue box. Remember that Part 2 states that if big F is any antiderivative of little f, that is, if big F prime of x equals little f of x, then the integral from a to b, little f of x dx, equals big F of b minus big F of a. In this statement, this little f of x is equal to big F prime of x, so let me replace it with big F prime of x. And we get the integral from a to b of big F prime of x dx equals big F of b minus big F of a. Remember one of our interpretations of the derivative of a function. If big F represents a quantity that depends on x, then big F prime of x is its rate of change. So what this equation is saying is that the integral from a to b of the rate of change of a quantity f of x dx equals big F of b minus big F of a, which would be the net change in big F between a and b. What big F is at b minus what big F is at a. That's its net change between a and b. This is a really useful way of looking at the Fundamental Theorem of Calculus, Part 2, and leads to lots of applications. Just as a quick example, for our first example, think about the following situation. Let's let t be the number of minutes past noon on some day, and imagine that you are filling up a pool by pouring water into it. Water is gushing out of a pipe, let's say at varying rates. Sometimes it's trickling out at like half a gallon per minute. Other times it's gushing out at 5.6 gallons per minute and so on. So that's a varying amount of water coming through at any time. Let's let r of t be a function that's equal to the number of gallons per minute that are pouring out of that pipe at time t, the number of gallons per minute being added to the pool at any time t. And as I said a moment ago, that rate of change, that could vary depending on the time t. Let's let big F of t be the number of gallons that are in the pool at time t. So the rate of change of the number of gallons in the pool at time t is equal to R of t, the number of gallons per minute being added to the pool. So big F prime of t is equal to R of t in this setup. So our interpretation of the fundamental theorem of calculus, part 2, from here, in this situation, would lead to the following. Imagine you had an integral like the integral from 60 to 120 of R of t dt. That's the integral from a to b of the rate of change of a quantity big F of x, or in this case big F of t, and that's equal to the net change in that quantity big F between a and b, in this case 60 and 120. So this equals the net change in big F of t between 60 minutes and 120 minutes. It's the number of gallons added to the pool between times t equals 60 and t equals 120. So that was just a quick example of our new interpretation of the fundamental theorem. Let's move on to another example. And up at the top, I'll remind you of the basic point from the previous slide. The fundamental theorem of calculus, part 2, states that the integral from a to b, f prime of x dx equals f of b minus f of a, which we can interpret as saying the integral from a to b of the rate of change of a quantity f of x dx equals the net change in f between a and b. In this next example, I hope to illustrate two things. First of all, the fundamental theorem of calculus is something that you might experience in daily life if you look carefully. And secondly, the fundamental theorem of calculus is also something that's kind of obvious if you look at it in the right way. Consider this graph that I took from the Washington Post. It gives the total number of reported daily cases of COVID-19 for the first 13 months or so of the outbreak, beginning in March 1st, 2020, and going as far as March 31st, a year later. So in this graph, the horizontal axis is days, number of days since March 1st, 2020. At each day, there's a bar. It's a bar chart. And the height of that bar is the number of cases reported on that particular day. So you can think about this as being the graph of a function, y equals the cases per day on any given day. So in day 300, maybe right here, the height of that rectangle is the number of cases that were reported on that day, which looks like it's about 50,000 for that day. Let's let big F of x be the total number of cases x days after March 1st, 2020. So the total number of reported cases since this time right here. So if that's big F of x, then its rate of change would be cases per day. So this graph here, this y equals cases per day graph, is equal to f prime of x, the derivative of the total number of cases reported x days after March 1st, 2020. So now think about 2 days, say day A and another day B that's sometimes later. And imagine taking the definite integral from a to b, f prime of x dx. Remember, this is the graph of f prime of x. So you would think about that as the area under this curve of f prime of x between times a and b. And think about that area. It's made up of a bunch of rectangles. Think of any one rectangle. Its base is 1 day. So its base is 1, and its height is the number of cases that were reported on that day. So its area, base times height, is equal to the number of cases reported on that day. So if you add up all of these rectangles, the areas, you get the total number of cases reported between day A and day B. You get the total new cases between day A and day B. In other words, the net change in big F between day A and day B. When you think of it like that, in terms of rectangles and their areas, suddenly the fundamental theorem of calculus may seem very obvious that this equals that. And it is kind of obvious. So granted, in this example, it's a little bit of a stretch because in calculus we deal with continuous functions, and this is a discrete function that jumps up and down. It's like bars, not a continuous curve. But still, if you see the fundamental theorem of calculus in this example, it's not much of a stretch to believe that it happens for continuous functions, the kinds of functions we deal with in calculus. So I hope this example sheds a little bit of light on the fundamental theorem of calculus. Let's now examine how our new interpretation relates to motion on a line. Remember the setup where we have an object, like for instance a car, moving on a straight line, and its position at time t is given by a function s of t. Then the velocity of that object at time t equals s prime of t. And let's think about that in terms of the fundamental theorem of calculus. S is an antiderivative of its derivative s prime. So the fundamental theorem of calculus part 2 says that the integral from a to b of s prime of t dt equals s of b minus s of a. And this s prime is velocity v of t. So in essence, this equation states that the integral from a to b of velocity dt equals s of b minus s of a, which is the net change in position between times a and b. And I'll illustrate that with a graph. Think about the graph of velocity v of t that's shown here. This is not the graph of position, it's the graph of velocity. And imagine you have two times a and b. Think about the definite integral from a to b of v of t dt. If velocity is positive on the interval from a to b, in other words, this object is continuously moving to the right between times a and b, then this definite integral represents, or is, the area under the graph of velocity. And according to our equation, it equals s of b minus s of a, which is the distance traveled between times a and times b. Where you are at b minus where you are at time a is the distance traveled. So you can see here an interesting connection. If you graph velocity and look at the area under the graph of velocity between a and b, that's equal to the distance traveled between times a and times b. The net change in position. But be a little bit careful how you interpret this, because it could be that velocity is not necessarily positive for all values of t between a and b. Maybe velocity turns negative. Let's say at some time c right here. The velocity suddenly becomes negative. Well, that means this object was moving to the right until time c, and then it went backwards and started going back. So the definite integral from a to b of v of t dt still equals s of b minus s of a, but now we would interpret that as a up minus a down. So you get a negative contribution there. Still, s of b minus s of a is the net change in position But notice it's not necessarily how far that car traveled. It's just the difference in position between time B and time A. What happened here is the object moved to the right until time C, and then it started going back towards where it started. So when we say net change in position between time A and B, that means the difference between where the car is at time B and where it is at A. And it could well happen that that net change was zero. This car might have gone back to where it was at time B. It was exactly where it was at time A. Could be zero. The net change could be even negative if it went back this far at time B. So be careful how you interpret that. Net change means S of B minus S of A. Let's do an example. Imagine that a ball dropped off a bridge at time t equals 0 has a velocity of minus 32t minus 5 feet per second at time t. And it hits the ground when t equals 2 seconds. Given this information, the question we want to answer is, how high is the bridge? Well, here's a picture. You've got a bridge here, and up at the top at time t equals 0, this ball is dropped off the bridge, and 2 seconds later, right there, it hits the bottom. So the question is, what is the distance from here to there? That's the distance between where the ball was at time 0 and where it is at time 2. Well, here's a solution. You can think about the height of the bridge as being given by the change in the ball's position between times 0 and 2. Then the net change in position would be the integral from 0 to 2 of v of t dt. That's the integral from 0 to 2 of minus 32t minus 5 feet per second dt. And you can work out this integral very easily with the Fundamental Theorem of Calculus Part 2. Take an antiderivative of minus 32t minus 5 and go from 0 to 2, and you get an answer of negative 74. So the net change in position was negative 74. The position at time 2 minus the position at time 0 was negative 74 feet. And remember, velocity here is negative because the object is moving down. This would mean the bridge was 74 feet high. And that's the answer. So you may want to work some examples like this to make sure you have a grip on it. Finally, let's move on to the last item on today's list to say more about the Fundamental Theorem of Calculus, Part 1. Now, granted, Part 2 is the most useful formulation, but let's not forget about the Fundamental Theorem of Calculus, Part 1. It states that if f is continuous on the closed interval from a to b, then the derivative of the integral from a to x, f of t dt, equals f of x. This is most easily visualized if you think about the situation in which f of t is positive on the interval from a to b. So the integral from a to x, f of t dt, gives this shaded area. And you can clearly see that that shaded area is a function of x. As x changes, the area changes, the value of this definite integral changes. It's a function of x. And the Fundamental Theorem of Calculus, Part 1, you can really look at as a derivative rule. It says that the derivative of this function of x equals f of x. Stated perhaps more succinctly, the derivative of the area under a function equals the function. Or alternatively, the area under a function is an antiderivative of the function. Let's look at an example of this. Think about the integral from 0 to x cosine t dt. So that's a value that depends on x. It's a function of x. So we're asking for the derivative of that function of x. Well, according to the Fundamental Theorem of Calculus Part 1, the derivative of the integral from 0 to x of cosine t dt should be equal to cosine of x. So there's our answer. We got it in one step. I want to point out here, however, that there's an alternate way to do this particular problem, because if you just look at this definite integral right here, we can evaluate that with the Fundamental Theorem of Calculus Part 2. The definite integral from 0 to x cosine t dt, this expression between those square brackets, equals an antiderivative of cosine of t, which is sine of t, from 0 to x. So we're looking at the derivative of sine of t from 0 to x. Plugging in the x, we get sine of x minus the sine of 0. We're looking at the derivative of sine of x minus sine of 0. Now sine of 0 is 0, so it's just the derivative of sine of x. And one of our derivative formulas says that's cosine of x. So we got this answer in two ways. First of all, using the Fundamental Theorem of Calculus Part 1. We got it in one step. But then alternately, we used Fundamental Theorem of Calculus Part 2 to actually work out this definite integral and then take its derivative. But think about this one, the derivative from 0 to x of this complicated function of t dt. We would be hard-pressed to work out the integral from 0 to x of this big function dt using Fundamental Theorem of Calculus Part 2, as we did up here, because I don't think you'd be able to find an antiderivative of all of this. However, look at the structure of this problem. The derivative of the integral from 0 to x of some f of t dt. Fundamental Theorem of Calculus Part 1 says the answer is just going to be f of x. So you take this entire function here, that's all a function of t, and just replace all of those t's with x's, and there's your answer. In one step, we got that derivative with the Fundamental Theorem of Calculus Part 1. Another example, the derivative of the integral from x to 2 of t sine of t over e to the t dt. Well, this looks like something we should be able to apply the Fundamental Theorem of Calculus Part 1 to. You would expect to get an answer of just take this t sine of t over e to the t and change all the t's to x's and put that there, and that would be your answer. But be real careful here. This derivative of this function, it doesn't quite fit the form of the statement of the Fundamental Theorem of Calculus Part 1. In that situation, the constant is at the bottom, it's the lower limit of integration, and the variable is the upper limit of integration. And down here, it's reversed. So this problem doesn't quite match the statement of Part 1 because the x is at the bottom, not the top. But no problem, you can overcome that because one of our integral rules, our definite integral rule, says that if you interchange the limits of integration on a definite integral, bring the x up to the top and the 2 down to the bottom, switch them, it just changes the sign of that integral. So this problem works out to the derivative of minus the integral from 2 to x, t sine of t over e to the t dt. Now, if you cover up that minus for just a second, we have an exact match to the statement of Part 1. So the derivative of this integral is just going to be x sine of x over e to the x, and there's a minus that would come out in the constant multiple rule for the derivative, and we get minus x sine of x over e to the x. So sometimes when applying the Fundamental Theorem of Calculus Part 1, if the variable quantity is at the bottom, you need to interchange the limits and change the sign, and then take the derivative. Let's do another example. Here we want to find the derivative of the integral from 0 to x squared plus x of t cosine t dt. It doesn't quite match the fundamental theorem of calculus part 1. Sure, the variable limit of integration is up at the top, but it's not an x. And for the fundamental theorem of calculus part 1 to apply it, you just have to have a plain old x right there, not some complicated function of x that we have here. So let's think about how we might overcome this. In the statement of the fundamental theorem of calculus part 1 up here, let me change that variable x here, here, and here to a u. Doesn't matter what the variable is, so let's write the fundamental theorem of calculus part 1 as the derivative du of the integral from a to u f of t dt equals f of u. And now we can look at this function, this integral here, as a composition. It's really a chain rule problem. We're looking to take the derivative of the integral from 0 to x squared plus x t cosine t dt. We want the derivative of this function, but write it this way. Write y as the integral from 0 to u of t cosine t dt, where u is the function x squared plus x. Suddenly, we've written this y as a composition, and we want to find its derivative. So how do you differentiate a composition? With the chain rule, of course. So using version 2 of the chain rule, the derivative we're looking for, dy dx, for this y, will be equal to dy du, the derivative of the first function here, multiplied times du dx, which is the derivative of our function u equals x squared plus x. So let's work that out. First of all, the dy du, the derivative of the integral from 0 to u of t cosine t dt, by part 1 of the fundamental theorem of calculus, that's just going to be equal to f of u, in this case u times cosine of u, so u times cosine of u there, then times du dx, that's times this derivative, which is 2x plus 1. And we're almost done. This should be a function of x. We need to change all the u's to x's. U is equal to x squared plus x. So here and here, we plug in an x squared plus x. So we get x squared plus x times cosine of x squared plus x times 2x plus 1. And there's our derivative with the chain rule. One final example. The derivative of the integral from minus x to x to the fourth, t to the fifth, e to the t dt. What are we to make of this? Neither limit of integration is a constant, which is what we would need to apply part 1 of the fundamental theorem. Both limits of integration are functions of x, minus 1 times x, and x to the fourth. So what can we do? Well, here's an idea. This integrand, t to the fifth, e to the t, is defined and continuous for all values of x, or all values of t. So this integral exists no matter what its limits of integration are. So let's pick a t value. Let's say t equals 0, just arbitrarily, and break up this definite integral with one of our definite integral rules. The definite integral from minus 1 to x to the fourth, t to the fifth, e to the t dt equals the integral from minus x to 0, t to the fifth, e to the t dt, plus the integral from 0 to x to the fourth, t to the fifth, e to the t dt. Remember that definite integral rule that says this equals this? Well, once we've broken it up this way, we have a constant here and here in the limits of integration. And this is beginning to look like something that we could handle as in the previous example. In fact, this limit of integration at the top here, we want that at the bottom, so we can interchange the negative x and the 0 and put a negative in front of that integral. And now using the sum difference rule and the constant multiple rule, this works out to be minus this derivative plus the derivative of this integral. Now, both of these derivative problems here and here are exactly the type that we worked out in the previous example. Those are chain rule problems. Let's do them separately. Let's first of all take this derivative of the integral from minus x, from 0 to minus x, t to the 5th e to the t dt, and work that out with the chain rule. The function we want to differentiate is y equals the integral from 0 to minus x, t to the 5th e to the t dt, and that breaks up as a composition, y equals the integral from 0 to u, t to the 5th e to the t dt, where that u is equal to minus x. So the derivative dy dx that we're looking for, this derivative, by the chain rule, equals dy du times du dx. Now dy du is the derivative of this integral, which by the Fundamental Theorem of Calculus Part 1 would be t to the u to the 5th times e to the u. And that's multiplied by du dx, which is the derivative of minus x, which is just minus 1. So we're almost there. We need to plug in the u equals minus x here and here. And we get minus x to the 5th, e to the minus x times minus 1. And this minus 1 times the minus x to the 5th, that's just an x to the 5th, e to the minus x. So with the chain rule, we've just figured out what this derivative is. And let's write it down. Got that minus from here. And then this derivative is x to the 5th, e to the minus x. Then to that, we have to add this other derivative. And let's work that out separately down here. Once again, this is a chain rule problem. We're trying to differentiate the function y equals 0 to x to the 4th, t to the 5th, e to the t dt. We can break that up as a composition. Y equals the integral from 0 to u, t to the 5th, e to the t dt, where this u is equal to x to the 4th. So the chain rule says that the derivative we want, this derivative, is dy dx, which equals dy du times du dx. Now dy du is the derivative of this integral, and again the Fundamental Theorem of Calculus Part 1 says that derivative is u to the 5th times e to the u. And this du dx, that's the derivative of x to the 4th, that's 4x cubed. So this product is u to the 5th, e to the u, times 4x cubed. We're almost there. We just have to plug in u equals x to the 4th here and here. And doing so, we have our derivative. That is this derivative. So we're just going to complete our answer by putting it here. The only difference I'll make is x to the 4th to the 5th is x to the 20th. Doing that substitution, we have the derivative that we were looking for. This derivative is minus x to the 5th e to the minus x plus x to the 20th e to the power of x to the 4th times 4 times x cubed. A rather complex problem, but breaking it up into simple pieces as we did here, it's really not that bad. So get some practice with problems like this. And that's it for today. We've reviewed the Fundamental Theorem of Calculus Part 2 and looked at an interpretation of it that says the integral from a to b of the rate of change of a function equals the net change in that function. And we've reviewed the Fundamental Theorem of Calculus, Part 1. Looking at the Fundamental Theorem of Calculus, Part 2, which is the most important version of the Fundamental Theorem, I want to emphasize that we now have a formula for finding definite integrals. Success in using that formula involves finding an antiderivative of little f. So it's very important at this point to apply the Fundamental Theorem of Calculus Part 2 to have lots of antiderivative formulas or integral formulas. In our next lecture, we're going to continue talking about integration rules or integration formulas. We'll talk about the substitution rule, which is an integration rule that works for more complex integrals. So get some practice, and I'll see you then. Goodbye.